Can't talk without slides, sorry. Well, let me say, first of all, it's just wonderful to be here, so thank you very much for the opportunity to speak to the How Coalition. I'm a huge admirer of what this group does, and as I was listening to some of the previous remarks and people's personal history, I was reminded to say that I grew up in London, Ontario, and we had a cottage at Grand Bend on Lake Huron, that's just north of the Plenary, and so my summers and my early years were spent playing in the sand dunes, playing in the lakes, being around the coastal areas of the Great Lakes, and I still, every chance I get, my family and I do our recreation around the Great Lakes, so it really is something that I care about a great deal, and so I really appreciate all the work that so many people are doing. So the title of the talk is Prioritizing Great Lakes Restoration. I'm going to describe some work that's being done by a shared credit that is looking at the ways in which we might try to think about all the different factors, stressors, or threats that influence the Great Lakes in a systematic way. So let me give you just a roadmap to the talk. I'm going to do a quick overview of major threats to the Great Lake. If you like, you can just visualize that wonderful video that was shown yesterday that starred Andy, among others. I thought it was a great summary of the issues in the Great Lakes. But I want to give you a quick overview, and I'll say why as I get into it. Then the body of the talk, assessing the relative magnitude and spatial distribution of multiple stressors, trying to look at all the different factors that influence the Great Lakes. And then I'll try to bring it back to the prioritization of Great Lakes restoration. So when we look at threats to the Great Lakes, there are so many of them. There's Nonpoint runoff, there's toxics, there's invasives, there's coastal development. The list is long. These are changing in importance over time. And I really appreciated Bill Rustam's remark reminding us of the history of factors that we've been concerned about for a long time and of the improvements we've made in many. So there's due to a great deal of effort by many in government and in NGOs and elsewhere. So some of these threats are being abated. Some are not, and we have new ones that are increasing. And they differ a lot by location, and we're all about spatial analysis in the work that I'm going to describe to you. But just obviously the upper and lower lakes are not necessarily influencing the same level of human impact, and they're not necessarily being influenced by the same factors. So, key point to set the stage for where I'm going in this presentation, there are multiple stressors at work, and their relative strength varies from place to place. It's a challenge for us to wrap our minds around all of these different things that are going on. I'm going to use this word stressor throughout the talk, and so I thought I'd better give you a definition. I use stressor and threat and risk pretty much interchangeably. We're not necessarily talking about change in the ecosystem, we're talking about pressures on the ecosystem. And here's I think a useful definition, because it says anything can be a stressor when it's outside the range of its normal bounds, and when human activity creates changes in some variable that impacts the system. Typically, the source of the stressor is something we're doing, and if we really want to know the full outcome of this, we need some kind of metric of ecosystem response. We need a biodiversity metric, we need an ecosystem function metric to get a full causal relationship between stressor and response. I want to again clarify that we're focusing on trying to get a handle on the stressors in this analysis. So I'm going to just run through this list. It's probably a familiar looking list to you. You might summarize them a little bit differently. Or you might just say this is fine. As I go through this list, and I'm going to do it just briefly because it's kind of a stage-setting exercise, I would ask you to think about which of these you feel are most important. Think about how they might vary from place to place, and think about how they're changing over time, because I think all of those things are going on and all of those are important. Land runoff, obviously one of the major factors influencing the Great Lakes: phosphorus, nitrogen, sediments, pesticides, other agricultural chemicals coming from both point and non-point sources. This has been an issue since the late 1960s. It was the loading of phosphorus from both point and non-point sources that resulted in the very apparent cultural eutrophication of Lake Erie in the late 1960s, those headlines that Lake Erie is dying or Lake Erie is dead, and a really wide suite of responses. Extensive and expensive responses. So it set off a lot of activity in upgrading wastewater treatment plants. It led to detergent bans gradually over the years. It led to combined sewer overflow controls that are still being implemented today. And it led to a lot of farming practice changes, focused primarily on erosion control to minimize phosphorus runoff and fertilizer management. There's been a lot of progress, and yet we see again a dead zone in Lake Erie. We see harmful algal blooms. That is not an energy drink, by the way. You would not want to consume that. That's largely microcystis, and the city of Toledo spends a lot of money to take it out of the water supply. This is appropriately a Great Lakes priority to promote nearshore health. And so it's a widely recognized issue still with us today. And I just got one more image I had to show. This is last Monday. People are working on the various metaphors. This is spinach, this is pesto, this is pea soup. But look at the wake of that boat going through western Lake Erie, and all you see is green. Toxic chemicals. Another area with a long history. One milestone, obviously, was the Cuyahoga River catching fire. And there's a wide variety of chemicals, persistent chemicals of diverse origin, industrial, agricultural compounds, heavy metals. We know that some of these bioaccumulate and biomagnify. We have food consumption, fish consumption advisories for at-risk populations, pregnant women. And again, I'm going to hit this theme of extensive and expensive responses because I want to come back to it at the end of the presentation and say, you know, how much better it would be to be preemptive to avoid these problems occurring. We have, however, seen the sunsetting of a variety of compounds like PCBs. We've seen air emission controls to minimize mercury release from power plants. Wastewater treatment plant upgrades, hazardous site cleanups, a lot of work on the areas of concern. So progress is being made. We still have legacy toxics, and we have emerging chemicals like pharmaceuticals and others. Again, appropriately, a Great Lakes Restoration Initiative priority. Invasive species tend to get a lot of the attention today, those Asian carp knocking at the door in Chicago. And you may already know this, over 180 species have been established. The graph that you see on your right from a paper of Tony Ricciardi's is one I quite like. It looks like a pretty steady rise from 1840 to the present. In fact, if you just do the calculation on that curve, a new invasive species will be identified every 28 weeks. And the Great Lakes is arguably the most invaded aquatic ecosystem on the planet. There is progress here as well. That rate of increase is slowing. We've come to recognize how important ballast water introductions have been, especially since 1959. And there's been significant progress to control ballast water introductions. I thought I'd just make the comment, because it might not be widely appreciated, that many invasive species are relatively benign. And as the field of ecology has turned more and more to trying to understand what it is that allows species to become invasive, we realize how hard it is to make predictions about the potential for a species becoming harmful. And we increasingly use the word invasive to indicate more than a non-native or exotic species, but one that actually causes economic or environmental harm. And people use this very rough rules of 10, a 10% rule, that probably 10% of the species that come knocking on the door actually become established. Probably 10% of those really become abundant, and probably only 10% of those really become invasive, seriously harmful. So we need to do a better job of understanding that process. And indeed, I like this phrase, the good, the bad, and the ugly, when we talk about invasive species, because we have invasive species that we love. The rainbow trout is an invasive species. The steelhead is non-native to the Great Lakes. You don't hear too many people calling for its elimination. Some are ambiguous. The alewives that were mentioned earlier that caused so much trouble with the die-off on the beaches have gradually become integrated into the food web. They're principal forage fish for Chinook and coho salmon. But they're also a problem because they like the eggs of yellow perch, walleye, and other nearshore spawning native fishes. The round goby, a relatively recent introduced species, is one that causes significant problems feeding on the eggs of native species. It's a major conduit of avian botulism to piscivorous fishes, but it scarfs up zebra mussels and smallmouth bass love them. So there's a need to sort of filter through the invasive species to determine which ones deserve our attention. Again, extensive, expensive responses, the chemical controls of sea lampreys, the wonderful progress primarily through policy and legislation to control ballast water introductions, the electric fences that are in the Des Moines River. Again, appropriately, a priority of the Great Lakes Restoration Initiative. Coastal development and habitat loss is really a smorgasbord of issues that influence the Great Lakes. Impervious surfaces in the built environment, which cause runoff of pollutants, shoreline hardening, piers and breakwaters that are part of protecting our commercial infrastructure. Port operations, so valued commercially, and the channel dredging that keeps ports open. Thermoelectric facilities, which keep the lights on in this room and pull significant water from the Great Lakes and cause fish kills in the process. And our responses here are largely regulatory efforts, zoning, industrial permitting, and so on. And these are really hard issues to deal with because all that infrastructure has real economic value to society. There's a lot of real-world constraints in trying to deal with these issues. Again, appropriately, a Great Lakes Restoration Initiative priority. Fishing pressures we don't hear as much about today, but the fish assemblage of the Great Lake has changed greatly over the last century and a half, and some of that has certainly been due to overfishing. Historically, this was an extremely valuable resource. It still is valuable today, both as commercial and a recreational fishery. But overfishing was one cause of declines, and then we had invasive species as well as nutrient enrichment, which has caused further changes. Today, this is extensively managed, again, an expensive operation. We have real successes, recovery of the lake trout in Lake Superior, for example, so that stocking is no longer pursued. Looks like incipient recovery of lake trout in Lake Huron, but we're not doing very well with lake trout recovery in the other lakes. So we keep busy trying to maintain this system in the best condition we can. Water withdrawals is an interesting one because there's so much attention from the compact to the water withdrawal topic. And you may disagree with me on any of these, so feel free to do so. We'll have time at the end for discussion. It's actually hard to get good numbers on how much water comes out of the lakes. You can get good numbers on the total withdrawal from the basin, but most of it actually comes from rivers, streams, and groundwater. The uses, the big user is thermoelectric cooling, water which passes through power plants and returns back to the lake. Public supply is relatively small in comparison, and consumptive use, that is the water that we remove from the basin and doesn't return, either because we incorporate it into products and export it, or because it goes by evaporation of the atmosphere, is only about 5%. So I'm going to say that within basin water use is probably a minor concern for the ecosystem. Maybe a concern for a municipality where they're getting their water from, but for the ecosystem, it's probably a minor concern. We've heard a lot about the concern over out-of-basin diversions. There's been a lot of success in the policy world through the Great Lakes Charter, its amendments, and the Great Lakes Compact. So it's pretty hard to export water out of basin right now. So this may be a concern that we should put lower in the rankings. And the last one I'll mention is climate change. This is one that's on everybody's mind, I think. It's a very interesting one to consider. Since the 1970s, we have clear evidence of changing climatic conditions in the Great Lakes. We have rising air temperatures, more dramatically in the northern basin than the south. Summer water temperatures are warming faster than the air temperatures, especially in Lake Superior. And winter ice cover has declined at specific locations. A caveat that I think is worth mentioning is that if you look at the record from 1940 to 1970, you see cooling. And so if you take 1970 as your baseline and move forward from that, you see a number of statistics that demonstrate climate conditions changing, but really if you look from 1940 to 1970, you'd see something more of this shape. So are we actually seeing the effects of global climate change, or are we seeing local long-term cycles is an issue that I think remains one that we have to think hard about. I do believe, however, that climate change is happening. I'm a firm believer that greenhouse gases from human activities are changing the climate, and the predictions that show us climate change over the next 30, 50, 70 years, I think are persuasive that we can expect changes in many variables: water temperature, ice cover, precipitation, lake levels, and these will have knock-on consequences for the biota and the ecosystem. Hard to respond to climate change. Mitigation, which is the effort to slow the rate of climate change, primarily by reducing the increase of greenhouse gases, is really a national and global effort. Adaptation, which is living with climate change, is something that really does make sense locally and regionally. And I'd be interested in people's thoughts on adaptation. Often adaptation has a human element to it. So for example, if lake levels rise and storms become more severe, we'll be worried about shoreline erosion. Our response will probably be shoreline hardening. If lake levels fall, we'll be worried about ships being enter our ports and follow their shipping lanes, and our response will probably be dredging. So adaptation may help human commerce. It may not be good for the ecosystem. And finally, for many things, it may be hard to do anything. So climate change is that big wild card that we see coming, that will influence everything else, and yet is still relatively hard to predict in specifics. So to return to my opening point of multiple stressors, there's 7 or 8 of them there, depending on how you count them. Each of those is actually an umbrella. Climate change is changing temperature, changing ice cover, changing precipitation, changing water levels. Each is an umbrella. Some are likely to be more important than others. Few will be equal, if any, will be equal everywhere. So now leading into the work that a team of us have been attempting, how do we assess the cumulative influence of multiple stressors across the Great Lakes as a whole? So this is Project Gleam. Andy is a member of it. We have a team of scientists from the US and Canada, representatives of the Great Lakes Commission, National Wildlife Federation, Michigan Sea Grant. So it's a diverse group of individuals, grateful for funding from the Herb Family Foundation. And I want to lead into this now by taking you through the main steps that comprise our project. So the first step in our project is to try to map the intensity of multiple stressors across the Great Lakes surface. In fact, to back up a moment, one of the things that got me interested in this work is I've done a lot of watershed studies and a lot of land use analysis, and this has become very common now by NGOs and scientists trying to assess threats across the landscape. And you've probably seen these wonderful or scary maps where you can see where the agricultural land use, you can see where the urban area is, you can see the roads, you can see the power lines. But when you come to the Great Lakes, you see 5 blue blobs. It's really hard to think about how all that land stuff influences the lakes. So our goal was to see if we could actually project onto the lakes the influence or intensity of multiple stressors. And then, it's clear that they're not equally important. So we wanted some way to develop rankings or weightings of the relative impact or relative importance of each stressor. And we did this by an expert judgment process I'll tell you more about in a moment. In fact, many of you may have suffered through the survey that we used to do that. And then we put these together. We combine our individual stressor maps, weighted by their relative importance, into a single cumulative stress analysis. Stressors had to be ones we could map at a 1 square kilometer resolution, so there's data limitations here. We wanted to cover all 5 Great Lakes because we wanted a relativistic view of stressor influence across the Great Lakes. So we could have a wonderful data set from Lake Michigan, but if we didn't have any matching data from other lakes, we really couldn't work with it. And by the way, we left out the connecting waters because of data limitations. So the St. Mary's, St. Clair, Detroit River, and Niagara River, and we stop at Kingston, we don't go out in the St. Lawrence. And for a stressor to be meaningful to us, we had to be able to say something about the action of that stressor, because sometimes you measure something and you're not quite sure what it's measuring. So we wanted to be able to identify a distinct pathway of impact for each individual stressor. So I'll let you dwell on this for a moment. This is the list that we came up with, and they're organized around 8 major categories, which are similar to the ones I ran through already: aquatic habitat alterations, climate change, coastal development, fisheries management, invasive and nuisance species, non-point source, toxics, and water withdrawals. This was a wish list. It was a wish list that our working group developed, had 50 stressors in it, and they were ones we thought we had at least a shot at getting data for. If it's in blue, it's finished and it's in today's presentation. If it's in green, we're still cranking the numbers. If it's in yellow, then we're probably, well, there's 1 or 2 of those that we haven't given up on. I think we're still going to get a HAB data layer. But some of these others were ones that we frankly couldn't get good data to map. If any of you have solutions for us for ones that we're missing, please talk to me after the presentation. So you can see, again, this point that there's a wide array of stressors, and we often, in the umbrella categories we use, we actually combine many of them into one that may not be homogeneous. So I'm going to show you a few of these. I'm not going to show you them all. Before I do that, a little bit about where data comes from. We were very happy to use other people's data. There's an awful lot of people who've given us help in this project, and Environment Canada's been terrific in providing information, among others. So sometimes it's a finished work of others. We can cite a study, the map's already been made. Often we just had to pull data together from a lot of sources, and we did a lot of actually developing data from web sources and Google Earth, and a lot of data crunching to get there. This is about 2+ years of work at this point. So I'm going to show you results for 3 major categories of stressors. So first of all, climate, one that people are obviously very interested in. We felt that there were 3 measures of climate change or potential climate influence that we could quantify. This one refers to the influence of changing water levels, and it's simply bathymetry. It's the area of the lake that's less than 3 meters deep. Doesn't mean lake level, we think lake level is going to drop by 3 meters, but that's the shallow parts of the lake where changes in lake level may affect the force of wave action on the bottom and as well as places where we're likely to have more wetlands. So that's the 3 meter zone of depth, and at the scale of this figure you can only see a few of them. Water temperature warming averages the rate of, it looks at water temperature warming using the July through September time window. These data are from 1990 or thereabouts to the present, and each point on that map, each pixel on that map is the slope of warming. And so what it shows you is that the greatest amount of warming is in Lake Superior, and that's actually consistent with other studies that people have done. I don't believe anyone has a 5-lake depiction of water warming, but this is consistent with what individual studies tell us, which is that summer temperatures are warming the most in Lake Superior and probably the least in Lake Erie. And the reason for that warming in Lake Superior, by the way, you say, why is that great big northern cold lake warming so rapidly? In summertime, what happens in lakes is you get a surface stratum, the epilimnion that forms as the water temperature warms in spring and summer, and you eventually get, as summer proceeds, basically a warm layer of water floating on top of the deep cold water. That surface warming process in Lake Superior is starting sooner, and it's actually setting the thermocline, the point of temperature break, shallower. And so there's an earlier and longer warming period of a shallower surface slug of water, and so it can actually absorb more heat. So it seems counterintuitive to you that Lake Superior is warming faster. That's the explanation. The third data layer shows an ice cover map, and that's from the 1970s to the present. And that shows decreasing ice cover days. Ice cover is being worked on by a number of people at NOAA. It's a difficult data layer to quantify well, but it shows the greatest decrease in ice cover around the perimeter of the northern lakes, again consistent with other studies that have been published. So if you look at this, you've got three indicators of climate change. I think they're all pretty useful ones to keep in mind. But again, emphasizing the complexities of the issue, these three data layers suggest that the effects of climate warming may differ among the lakes, and it will differ in different ways depending upon which aspect of climate change you think is influencing whatever variables you're concerned about. I'm going to show you some data layers for Nonpoint runoff. We have 4 of these that we've developed, and the one in the top left of the figure is sewer overflows. At the scale of the 5 Great Lakes, showing a thumbnail map, you can't see those very well. That's why there's a blow up on the left-hand side of the figure to show you the area around Milwaukee. These are highly localized. The other 3 maps are of phosphorus load, sediment load, and nitrogen load, and they look pretty similar. And the reason they look pretty similar is a significant amount of that load, of course, comes from tributaries. That's the runoff from the land. And so if you look at the Nonpoint source stressors, you can see some things that are unsurprising. They reflect the locations of major tributaries, the areas of intensive agricultural land use, and of course coastal populations. The last one I'm going to show you for individual maps is invasive species stressors. These are 4 we've developed with help from many. And so the one on the top left shows the estimated ballast water risk. This is a difficult item to quantify. The actual underlying data is the exchange or flushing of ballast water in recent years, excluding Lakers. And so this shows the locations where the most ballast water flushing is occurring, and therefore, presumably, the most potential for release of invasive species that are transported by ballast water. In the language of species invasion, we use the term propagule pressure, because invasion is this very probabilistic phenomenon. Most invasions fail. You probably have to have repeated infusions of whatever that invasive species is before it becomes established. We call those propagules, and so this is a measure of propagule pressure. The other maps may be a little more obvious to interpret. The estimated distribution of sea lampreys within the Great Lakes, the estimated distribution of round gobies. Both of those are modeled in different ways, and those are indications of where we think those 2 invasive species are most important. And then the descended mussel distribution is actually a data-based map where we essentially connect the dots from samples from people provided kindly by people from the NOAA lab, from University of Windsor, from some New York universities. So you get the message again that everything varies across space. These individual invasive species have distinctive distributions. There's not just one way in which invasive species are likely to affect the Great Lakes. So moving then to the integration of this information, what do we do with this mess of stressors? How do we put together the cumulative influence and have some sense of what that relative magnitude is? To do that, we used a survey process. How many people in this room remember a really, really long survey? Thank you. It was a bear of a survey that we distributed. I'll just give you the numbers in a moment, to get information from Great Lakes experts on their best judgment. We wanted to be able to provide weightings that were stressor specific. Is mercury twice as harmful as nitrogen? We wanted them to be habitat specific. Is mercury in wetlands worse than wetlands in the open water? And we wanted these to be people's best quantitative judgment. And so we gave them a fairly detailed kind of framing of what we meant by ecosystem impact or ecosystem influence based on 5 criteria. So how often does this stressor act? What's the spatial extent of this stressor? What's its ecological scope across the food web? All trophic levels, does it only hit one trophic level? Is it a big hammer or a little hammer? And then how long does it take the system to recover? And we had a social science developed scenario process that we used to kind of extract that information into a single score. And one of the things we tried very hard to do was get people to focus on current stressors. So we said in our survey, don't tell us about DDT unless you think DDT is a significant stressor today. Don't tell us about Asian carp if there aren't Asian carp in the Great Lakes. We tried to bound people as best we could to current stressors because we wanted to look at, indeed, what's happening now, not what we think might happen. Surveyed a lot of people. We identified researchers who were publishing regularly on the Great Lakes. We identified Great Lakes managers from lists we got from the Great Lakes Fisheries Commission and from other agencies. And we contacted, we believe, every single member of HOW, as well as additional specialists within the Nature Conservancy. Over 300 people started our survey, and we got partial information, and 161 spent at least an hour giving us very detailed responses. So we have a lot of data for this. So, are all stressors the same? Obviously not. Here's a rank order, and I'll show you which ones are at the top in a moment. But this graph just makes the point that at the right-hand end of your scale, you've got stressors you might want to think about that nobody believes are important. At the left-hand side of the scale, you've got stressors that go, that one really matters. What's at the top? Here's the top. We asked for the top 5 picks, and of course, not everybody picks the same top 5, so the list is a bit longer than 5. But here's what people put at the top: invasive mussels, ballast risk, coastal development, nonpoint phosphorus, invasive fish, a couple of climate change variables, lampreys, more nonpoint, harmful algal blooms. I think a pretty reasonable list, but I asked you to think about this as I started my presentation, and see if you agree or not. But this is a consensus of experts, and this is the information from which we derive a ranking or weighting term. We were interested in whether different audiences would see things differently. And so here's just a little more data that you might find intriguing. It's organized into the 8 main umbrella categories we used. The horizontal dotted line, if every bar was at that horizontal line, every risk would be identical. So you see invasive jump way above that line. Fisheries management and water withdrawals are way below it. So that's pretty much a consensus. There are some interesting differences. Managers seem to care a little more about invasive species than the researchers do. They seem to care a little bit less about nonpoint, and we'll be exploring that. And climate change came in kind of in the middle. So again, some thoughts about the relative magnitude as assessed by expert judgment. There was pretty good concordance. about ranking stressors by place, by approach. Some interesting differences we'll be writing about. Stressors varied widely in importance, and we were able to derive quantitative lake and habitat-specific measures. And we think this alone is useful information for decision makers to think about what their priorities might be. So finally, to put this information together, we basically multiply a stress value by a weighting. The stress value is pixel by pixel, each square kilometer across the surface of the lake. The weighting term is specific to the stressor, the lake and the habitat. Multiply them together. We normalize everything between 0 and 1 because it doesn't make sense to let the original scale influence the results. So everything gets put on a level playing field, and we add them up. And so there's a formula, and we project that onto the lake surface. Here is our current draft map. It's based on 33 stressors, and it shows profound differences across the lakes. This is a relative scaling. I'm going to make this point over and over because it's important for the interpretation. In this scaling, 20% of the values are red and 20% are blue. It just does a cumulative percentage, and it spreads things out from highest to lowest. So you can see that Lake Erie and Lake Ontario, clearly much more cumulative stress shows up there than in Lake Superior. In the nearshore zone, more than offshore. We wouldn't expect major surprises. We're trying to quantify things that we probably have pretty good intuition about. But I do want to emphasize, as I said, that the scale is relative. And I want to show you a second depiction which uses the actual values because it makes the point that things aren't quite as bad as the first map might lead you to suspect. If you use a linear scale, most areas score below 0.4 on a 0 to 1 scale. Moreover, as I've said before, I want to emphasize this is a map of stress or relative risk. It's not a map of actual impact. And so we see that, again, there's a range across the lakes, but most places are moderate. So I like these bar graphs. I'm sorry to get quite so data specific, but I think they drive home the point I was just trying to make. So this is the actual stressor values averaged by lake, showing a minimum and a maximum. And what you can see is, I think my little red dot's still working. So you can see that the value, none of the averages are above 0.4. So take that to be good. Lake Ontario has a higher value than Lake Erie, than Lake Michigan, and Lake Erie and Ontario are about twice Lake Superior. So I think it's pretty sensible in that regard. You can see that from the maximum values that you can find highly stressed areas in any of the lakes, and you can find relatively unstressed areas at any of the lakes, but you don't find very many low values in Lakes Ontario and Lake Erie. We also wanted to see how this played out by habitat, and so we developed a habitat map for the Great Lakes. And this is something, interestingly enough, doesn't exist or didn't exist, although there's been some previous work on Lake Erie, and there's some new work that's been funded to start doing nearshore habitat. It was interesting to us because we're used to work in marine systems where there's really distinctive sort of ecosystem classes, and it was something we had to work on for the Great Lakes. So we developed with the help of others the following categories. We put coastal, wetlands, and river mouths together. Many wetlands are associated with river mouths, and this is a sensitive, high-value nearshore habitat. The littoral is a technical term for the shallowest water, 0 to 5 meters. Sublittoral, 5 to 30 meters, and offshore pelagic, greater than 30 meters. So those are the zones that we use. And if you look at the cumulative stress by habitat, wetlands and river mouths rank the highest. They're around the 0.5 mark. None get a low rating, and again, you get high values for just about everything. But it shows, I think, convincingly and unsurprisingly, that river mouths and wetlands are more stressed than the littoral, which is more stressed than the sublittoral, which is more stressed than the open water. So I think we put some quantitative values on things that may well be kind of what we thought we'd see, but it's satisfying to see them. At some point, we plan to have this available on a website where people can zoom in and look at their favorite spot. We wouldn't want you to zoom in too close because this is really a tool that's useful for getting broad comparative perspective, but it is useful to zoom in and get an idea of where are the places that have the highest level of influence from multiple stressors, where are the areas that are lowest, and it reminds you of the spatial and local variation. So, finally, bringing this around now to the issue of prioritizing restoration and conservation opportunities for groups like this and others to work with. Again, I think this fits with the Great Lakes Restoration priority of working with partners, working for solutions. The Great Lakes really, I think, arguably pose some very special challenges. One is scale. The Great Lakes are large, and I'll show you a map in a moment. They're large relative to most other restoration targets. We're taking on a really big challenge when we talk about restoring the Great Lakes. It's a very complex system. The wide range of threats or stressors relative to most other restoration targets, again, is an important point, I think, to make. Now, people in the Chesapeake Bay would say, yeah, we have overfishing and we have nutrients and we have coastal development. It's true, but I think we try to struggle with many different threats, which brings us back to the challenge of prioritization. Thank you to the Michigan Sea Grant for this map. It makes that point of scale rather nicely. You can fit the Everglades, Chesapeake Bay, Puget Sound, this North Carolina restoration site. You can plop them all down in the Great Lakes and have a lot of surface area left over. We're dealing with a really big system. As a researcher, I obviously believe that restoration priorities should be data-driven, and that while we know a lot now, we do a lot of good work based on. A lot of this is obvious. You know, we look at areas of concern, we look at hardened shorelines, we look at polluted rivers. We know we have to work on them. The areas that are being focused on for nutrient control across the Great Lakes. That was mentioned yesterday by an EPA official. Great picks. I think people are doing the right things already, but I think we can always use this information. I think to think harder about it. You've already seen our work. I also wanted to mention the work of the team that Lucinda Johnson at the University of Minnesota Duluth leads, which is a land-based assessment. They've now got a paper in press filling in the Canadian side where they've developed a variety of environmental indicators for land-based stressors. And in fact, we collaborate across our two teams, and one of our future plans is to see how well these two actually work together and match up. I think data really is important for thinking about these threats. Which are most important and where? We can't just say, go out there and tackle invasive species. We have to be strategic about it. We have to realize that the relative importance of these threats varies from nearshore to offshore, from the upper lakes to the lower lakes, and we have to think about the cumulative influence as well. One obvious use of this kinds of information is it would be a mistake in a restoration project to address only one stressor if you happen to know or could find out that other stressors were acting in the same location and perhaps were of greater importance. So if our goal is to restore a system rather than remove one stressor, we have to think about the way in which multiple stressors might influence our targets. And then we shouldn't lose sight of our conservation opportunities, because the same spatial information that tells you where your restoration needs are also tells you about the areas that you might want to highlight for protection and stewardship. It might be the last good representative of a certain kind of wetland ecosystem. It might be the healthiest river mouths that we have still in Lake Ontario, and so it can help us with those sorts of questions. I was involved in a river project that tried to take on the topic of sort of restoration principles, and I borrowed a little bit of those ideas. They're very general ideas, but I thought they might at least be useful for discussion. We really need clarity of goals. Mr. Rustin spoke of focus, focus, focus. We need to know what we want to achieve, and we need to stay targeted on it. But we have to also know what is feasible to achieve. And we also have to be clear on who is we. I don't believe that only scientists should decide what those priorities are. I think in the end, because we have to make choices and because we can't restore systems to their perfect original state, there really are societal decisions. How important is it to us to spend X amount of money to repair this versus another part of the system? Because we hope there's more restoration money coming in the next year, but it's always limited. It has to be spent wisely. We really need to do the sorts of things these conferences are great at, which is share information on what we're doing, learn best practices, and get consensus on that. Ultimately, we want to know what the ecological condition of the system is. So I've portrayed stressors, but actually a future step for us, again with partners for data that we're waiting to get, is to say, does this really map into the condition of the ecosystem? It's nice to reduce the amount of phosphorus coming out of a river, but you really want to make sure that you reduce the frequency of harmful algal blooms out there in the lake. And the long-term goal has to be a self-sustaining ecosystem. Strategically, we could do more with the precautionary principle. It's one of the things everybody in our business reiterates. We shouldn't be in crisis management. We spend a ton of money fixing things after they're broken, and we should be better at anticipating things. I think Andy Bucksbaum had a quote in the film, and trying to remember that quote, but it was, have to fix the things we don't see. We have to be, not get into fixing things after they become issues. We need, obviously, to prioritize risk. We can't do everything. Place matters. That's really the theme of the work that we do, what we've tried to bring to the good work that so many people are doing on the Great Lakes. We've tried to bring this spatial focus. This is a preliminary effort, obviously. We'll be continuing to improve it. Others will be hopefully spurred to improve it as well. But recognizing that the types and level of threat varies with location reminds us that we need good spatial information. And networking is the way in which we are able to really make rapid progress. We've benefited enormously. I can't tell you how pleasantly and wonderfully surprised we've been by people's willingness to share data and willingness to buy into a project that's a little bit out there in terms of what we're trying to do. But the best scientists working on virtually every topic area we've contacted have said, yeah, we can help you with that, or that's not ready yet, but we think what you're doing is worth doing. So just emphasizing that this work has been done with the help of many. Our core working group spread around the Great Lakes Basin, US and Canada. Key team members, a number of whom are here today, Sigurd Smith, Pete McIntyre, Chris Joseph, Adrian Marino, and Alex Prusovich. We've had some great help from students. We've gotten data from just about everybody. And if you have anything to share that might help us move forward, please contact us at these emails or visit our website to learn more about our project. So that's the end of the presentation. I'd be happy to try to take questions if you like.
And you have been watching live coverage of Great Lakes Now right here at greatlakesnow.org on Detroit Public Television.